I do want to say also that clam landings regained their place as the second largest fishery in the state this year. The landings are coming out. I think they came out yesterday, maybe. Ours went down, so we're second best. I'm going to introduce Bridie McGreevy. She's a research fellow at the New England Sustainability Consortium, and she's based at the University of Maine Orono. She asked me to give a little bit of an introduction. I'm going to let her cover what the NEST program is. She'll explain that to you guys, but what I do want to say is the department and the university and other research institutions, we're trying to partner more actively and more effectively on projects where we can get input from industry and stakeholders on the issues that they want worked on, and then collaborate between the department and these research institutions like the University of Maine to really get the expertise that we don't necessarily have in-house to address these problems and get some really meaningful results that we can then use in management. So without further ado, right. Standing in the back, we do have some seats along this edge if anyone's interested in listening. Great. So, thanks for your patience. So that will switch around. Again, my name is Bridie McGreevy, and I'm a postdoctoral researcher with the New England Sustainability Consortium. The acronym that I'll be using is NEST, which is a little bit of creative work with the T in consortium there. I study communication and collaboration, and my role within NEST is to help study and facilitate some of the research partnerships that we'll be highlighting today. So NEST is composed of more than 75 faculty and students at University of Maine, University of New Hampshire, other state and private colleges in Maine and New Hampshire, and it also includes more than 15 different academic, governmental, and non-governmental institutions. You can see some logos from some of our key partners here: Maine Sea Grant, DMR, DEP, MDIBL, Biolab, Maine Healthy Beaches, and others. Oops, let's just have an animation here. So the NEST project grew out of previous investments in Maine and New Hampshire
to do sustainability-related work. In Maine, this was through the Sustainability Solutions Initiative, which created a statewide network for sustainability science in Maine, resulted in things like the tidal power turbine that's in Coscook Bay, emergency action planning for invasive species, landscape scale plans for wetland conservation, among many other types of outcomes. In New Hampshire, this is through the Ecosystems and Society Project, which is ongoing and resulting in a statewide network for environmental sensing technologies. So UMaine and UNH got together in what's called a Track 2 EPSCoR, and our goal here is to build the capacity of universities to strengthen connections between science and decision making. So it's that linkage between science and different types of decision making contexts. And our first project is the Safe Beaches and Shellfish project. So we're focused on bringing science to decision making for beaches and shellfish. We're using what's called a sustainability science approach, and the key question that we ask within sustainability science is how do we do science in ways that will help solve societal problems? We start out by trying to figure out, well, what are the needs? What are the problems people are working on? And how through different types of collaborations across disciplines and with a whole bunch of different institutional partners can we bring different types of knowledge to bear on these problems and develop solutions together. So the presenters will be talking now, will be highlighting this applied approach to science, sustainability science, and I'll just introduce each of them now. Dr. Teresa Johnson and Elizabeth Maxwell, both from the School of Marine Sciences at University of Maine, will be highlighting some of their social science research with members of the Shellfish Advisory Council on threats to the industry and perceptions of threats. And then we'll have presentations from Dr. Kate Beard-Tisdale, who is also at University of Maine Computing and Information Sciences, Dr. Damian Brady and Dr. Kelly Cole in the Darling Marine Center and School of Marine Sciences, and then finally Dr. Brian Beal, University of Maine-Machias, and the Down East Institute. And our goal here is first to describe the science, and some of this research is still in process, so to provide an update to some of the core people who have been involved in this research as it's moved along. And then we want to have time at the end for panel discussion, and the discussion will focus on identifying additional needs for applied marine science, focusing on data gaps that we know about, opportunities for future collaborations, and also best practices both on the university side and the researcher side, or on the partner side for applied science partnerships. Yeah, okay. So with that, I'll introduce Teresa. Come on up.
Thank you. Good morning. I very much appreciate this opportunity to share our research that we've been conducting over the last year or so. My name is Teresa Johnson. I'm a faculty member in the School of Marine Sciences in Orono. I am a social scientist, so I'll be presenting some of the social science research that we've been conducting with members of the shellfish industry. I want to acknowledge Elizabeth Maxwell as a graduate student with me in our dual degree program in marine biology and marine policy. She's been working very closely with me on this. So the goals that we have, this is part of a much larger effort, as Bridie explained, and what I'm presenting is also just a piece of a very larger social science project that we're conducting right now. The goal for today is that I wanted to identify some of the most pressing issues facing Maine shellfish industries, with the intent of providing some information for us to start this dialogue between university researchers and other stakeholders. Again, thinking about sustainability science, we need to know what the problems are. We need to know what people care about, what are some of the most pressing research needs, so that we can start working together to solve some of them. So that's my goal for today. So in order to start thinking about these, what are the problems, what are the threats that we should be concerned about in our research, we started by reaching out to key stakeholders in the shellfish industry, both in the wild harvest sector and the aquaculture sector. to start getting an understanding of what is most salient issues that we need to start thinking about. So we conducted 19 semi-structured interviews last summer with, again, a variety of stakeholders. We asked a lot of questions. It was, so many of you may have participated in those interviews last summer. We very much appreciate your contributions to our research. Your input was extremely valuable, and we very much appreciate it. I also would like to take a second and acknowledge some of the other participants in our research. Bridie helped with some interviews. Tyler Queering is here somewhere, and he participated as well, and Cameron Paquette were some of the folks that you probably talked to if you have participated in this research. So we conducted these interviews and we asked a lot of questions, but today I'm going to focus on answers to the open-ended question, what are the most pressing threats facing the industry here in Maine? So get really quickly into the results. Again, this is what we heard from you, right? These are what you told us were most were the concerns that you had regarding the industry. What you're seeing here is the percentage of all respondents that identified a particular threat. And so you can see these. I'm going to go through them one at a time, but no big surprises, right? And as I'll talk through these, many of them are very much interconnected. Right off the top, you can see that the most common threat that we heard from people are green crabs, right? That shouldn't surprise anybody. Everyone's, has been concerned about it for a while now. 79% of the people we talked to mentioned green crabs as something we need to be worried about and thinking about in terms of future research. So we heard about green crabs, but we also heard that last year was a cold winter, and maybe it's not as seemingly as an imminent threat as perhaps it once was. However, people were quick to note, this is because they died off because of the cold water, right? This is probably nothing new for you, but this is these are the things we heard over and over again in our interviews, and that's why I'm emphasizing them today. It was cold, right? But most people pointed out that, climate change is happening, temperatures are warming. So this isn't a problem that's just going to go away. We still need to sort of keep paying attention to it. It's not something that we should just forget about just because this year it might not have been a big concern. So in fact, 21% of the people we talked to specifically mentioned climate change as a concern, a threat that's facing the industry. Right, and as you think about it, as you can read through the other threats that were identified, many of these, the underlying concern is climate change, and climate change was often referenced when they talked about these things. So when they talked about green crabs, they talked about climate change, right? When they talked about ocean acidification, they talked about increasing other predators that were coming in, affecting recruitment, increasing disease, red tide. These all were, in some way or other, concerned about climate change. And not surprising, we heard a lot of the folks we talked to raise concerns about water quality issues and access issues, right? This includes all of the closures that we talked about this morning, the bacterial contamination closures, etc., pollution closures, as well as closures, conservation closures, and things like that are limiting a harvester's access to the resource. It also included access problems related to fishermen not being able to access the shore because of property owners not allowing them to walk on their property, right? So concerns in that way. So very, very, very concerned about those things. Not surprising. We heard a lot about this morning already. Underlying these threats, we heard over and over again this issue of population growth. We heard time and time again, the problem is there's too many people moving here, right? They're building houses, that's increasing runoff, increasing pollution, right? Again, leading to water quality issues, that are leading to closures and things like that that are the sort of underlying and very pressing threat. And also new people coming, buying property, not really having a history in the area, not really understanding what's going on in the industry, not wanting people to access their property, limiting access to the coastal zone. The next group of threats we categorized as policy or science issues, right? Some of the political questions that emerged in our interviews. This included concerns about how monitoring is being done, how science is being conducted, how decisions are being made regarding closures, a bit of uncertainty about how that actually works. How is the science being used? How is it being created to make decisions? This also included political and legal questions and issues concerned with aquaculture lease siting process, being able to get a permit if you want to set up a shellfish farm, the sort of paperwork burden, things like that, the uncertainties about that. And then threats arising from challenges with enforcement and other compliance issues that often undermine local management. And again, you can see that these are interconnected, right? That's one of the points that I had today. These affect both state and municipal levels of decision making, and they're about their underlying issues related to water quality, over harvesting, access, and then population growth. Specifically, a lot of the politics that arise from landowners' perceptions of the industry and their willingness to allow people to use their property. So these are very interrelated. And so at the end there, we heard some folks talk about concerns about recruitment, right? And you can kind of imagine, well, that's really important, right? That's really important, but only a couple people mentioned that, right? But if you look closely, and as we analyzed how they were talking about the different concerns and threats that they heard, they're all really talking about recruitment. All of these things are contributing to concerns about recruitment. Green crabs, ocean acidification, overharvesting, other predators coming in and eating up stuff, right? Climate change, questions about eelgrass, disease, they're all about things that are affecting recruitment, right? So really, recruitment is a very, very important concern that you all have, right? So based on these threats and concerns that we heard in our interviews with you, we identified there's some emerging research themes that come out strongly, right? There's need for research to improve recruitment, right, and affecting a lot of these underlying threats that I talked about. Research to improve municipal and state decision making, right, including municipal management related to stock assessments and improving the use of science in decision making, some of those issues. Research to minimize the impacts of population growth, including, again, impacts to water quality, but also impacts for harvesters' access, right? People need to be able to harvest the resource. And also research in thinking about, climate change, right? That's something that most people agree is something we have to keep paying attention to. So finally, these threats that we heard are very interconnected. They're very complex, right? We heard a lot of interest in working on these problems together, right? We need to start working together, communicating, collaborating, and there's just a lot of interest that we felt very, very timely considering the work that we've been doing. So we're here today, and we're hoping to continue this dialogue and communication. Elizabeth and I will be here the rest of the day and over the next couple of days. If anyone would like to chat with us more, we're continuing this work currently, so we haven't already talked to you. So thank you.
We'll have time for questions and discussion at the end. As we're setting up this next presentation, I also wanted to note that we have a more detailed agenda on the back table with a web link and contact information for all of us. Over on the side table.
Teresa mentioned that water quality was one of the issues of concern. And so that's where we've been focusing on, myself and my graduate student, Frank. And DMR has a very rich and maybe one of the most comprehensive water quality data sets right along the coast of Maine. And so our objective was to, in a sense, mine this data set and try to get a sense of, are there some patterns that we can sort of tease out in terms of the variations in the water quality and what that may mean for management decisions and closure decisions. So some of you may be familiar already with DMR's water quality sampling approach. So there are several growing areas that are defined, all of them down the coast. And there's observation stations. It's a stratified random sampling scheme. They're on the order of 2,800 stations that are observed approximately monthly. There are also extra samples. So when we have flood closures, there are follow-up samples on a regular basis to see where conditions have basically returned to normal and sites can be opened again. So we're looking at the data set runs from 1990 to 2013. And so overall there's over 300,000 observations in this data set. And so what's collected is a water sample that's then evaluated for fecal coliform. The tide level is also recorded, wind direction, water temperature, salinity, and a field called adversity. So this would be a code that would say, for example, this is in a marina, or there were so many boats locally, or there were so many geese, some wildlife, anything that might affect possibly water quality at that location. And key one being precipitation. So if there was precipitation in the last 24 or 48 hours, it gets a code of P to indicate that there was a precipitation event preceding the observation. So I'm just going to talk about, there's potentially many different factors to look at. And so today I'm just going to focus on a small piece. And what we're looking at here is, how do the responses to precipitation events vary spatially? So not every site is equal, and some might not respond to precipitation significantly, and some might be extremely sensitive to precipitation events. So that's what we were trying to tease out here. So what we did was we selected observations that were taken or associated with precipitation events. So specifically, these would be ones that had this P adversity code. And so there were 57,000 approximately of these observations, which were taken within 24 hours of a precipitation event. So again, we want to sort of look at these and say, again, are there differences in terms of how locations are responding to precipitation events? So we summarize these by the observation stations. Again, 2,600 of these approximately. And within these stations, what we're looking at is, for these observations, did they exceed the threshold fecal coliform level, which is 31 fecal coliform units. So that's a given threshold, and so how often do we see exceedances when we have precipitation events? So 559 stations had no exceedances. And 47 stations had greater than or equal to 20 exceedances. So we see a range here, again, of, in a sense, sensitivity to precipitation events. Some are really not showing a significant effect, and some are showing quite dramatic response to precipitation. So the maximum here was 42 exceedances out of 63 observations at a station in near Chidesport. Maybe. All right. So I don't know if this is. I'm apologize, this is a larger room than I guess I was anticipating, so it might not be able to read these numbers here. But I just point out a couple of key columns. So the first column is the stations. Each one has unique, these are the observation stations, each one has a unique number. Then the next one is the count of the number of observations. And then the other one, the number of exceedances. So these are all ones that had 0 exceedances. So these were observed during the precipitation event, and this is the average over precipitation events. But in all those cases, however many there were, in the case, say for example, there were 23 observations during precipitation events, never an indication that there was an exceedance of fecal coliform. And conversely, this is the opposite end. We see sort of those which have the greatest number of exceedances. So this would be an indication that these are the sites that seem to be really sensitive to precipitation events, where the previous set, again, is somewhat, I would say, insensitive, but not showing a response to the precipitation events. So we just take a little trip up the coast, so starting at the southern end, we're seeing at the kind of lightish dots are ones that were observed during precipitation events, and as the ones that are highlighted in blue are the ones that showed, in a sense, no response. So these had exhibited no exceedances for all the cases where they were observed during precipitation events. And so moving along, you can sort of see some somewhat interesting patterns. We see some clusters of places where there's no exceedance, and it tends to be, again, closer to more of an open ocean situation. And as you go up the river channels, we don't see that. So these are the ones, again, that are basically showing little response to precipitation events. And similarly, all the way up to the down east in Eastport. And again, we see some sort of interesting clusters of cases where we see no exceedance events. And then conversely, the locations where we see larger numbers of exceedance events. And again, it may be visible in the back, but one thing that we can notice from these that are showing exceedances is that they're often associated with the mouth of the stream. And we might expect this. If we have a precipitation event where we're going to see the most runoff generated is probably at the mouth of the stream. So that's typically the pattern that we see in most cases, but not all. Here we're looking at Bar Harbor. And again, no stream that I can see that's associated with that, but there may be storm sewers or something else that's actually hidden that we don't see in terms of the map. And again, this is pretty much we see the trend again from these locations which are showing the greatest number of exceedances are pretty much just routinely associated with streams, but not all streams, which again I think is also interesting. So some streams, we have an observation, set of observation sites at the stream, but they're not. So again, the difference in location does make a difference in terms of the water quality. And again, just another example, and here we're looking at the base of the Kennebec, which we might expect would really have some problems. Okay, so next step was we wanted to sort of look at this a little more statistically. So we did a t-test. We wanted to look at the difference between the mean and the log coliform counts for samples which had the p-adversity. So samples which were taken in the context of a rain event, a precipitation event, versus those that weren't taken in a precipitation event. Look at the mean of those coliform counts and say, are they significantly different? So our known hypothesis was that there would be no difference between these means. So 1,500 69 stations, or 63%, had non-significant differences. So there really was no difference between observations taken during precipitation and not. And 843, 34%, did have significant differences at the 0.05 level. And then 71 stations had significantly higher means for non-adversity, p-adversity samples. So in this case, again, the mean log coliform scores are actually higher for non-rain events. So this is kind of interesting. So we're seeing, again, higher mean scores for some of these sites, irrespective of the rain event. So again, so something else is happening in terms of water quality at these locations beyond precipitation. So these are examples of stations which had, again, significantly higher means for non-p-adversity samples. So again, samples that were taken not with respect to precipitation event. And this makes some sense. These are, again, not associated with a stream, a river channel. So there's something else that's, again, that's driving the water quality issues besides runoff from the stream. So on the other side, 2,042 stations out of 2,502 had higher means for p-adversity samples. So these are ones, again, that had, they're showing the most impact in the case of rain events, precipitation events. 764 stations had significantly higher means for p-adversity samples. So in this case, again, the mean log coliform scores for coliform were significantly higher for rain event samples. So this would suggest that these are locations where there's a high sensitivity to precipitation and rain events. And these are just examples of these locations, which again are showing, it says high sensitivity to precipitation events. And for the most part, again, we can see that they are associated with streams. Not all of them, but that seems to be sort of a general pattern. And yeah, the St. George. These again are ones showing high sensitivity to precipitation events. In this case, the red dots are ones that are very significant. They're all significant, but the red dots are very significant. And just another example from farther south. So some of the next steps that we're interested in is looking at the flood closure analysis. So what happens post a precipitation event? And do we see differences in terms of recovery time? How long does it take a site to recover? Do some sites take just a few hours, a day? Do some take several days? So kind of looking at the spatial differences, seeing what's driving it in terms of recovery times. So that's one piece, and the other is to look at some more detailed analysis of the precipitation data. So at the moment we just have a P code that says a precipitation event occurred, either just before or at the time an observation was taken. And we'd like to be able to correlate that with some more detailed precipitation data that we've acquired independently from the National Weather Service, the COCOROS, which is a citizen science contribution of precipitation data. And so we can see this is an example of the weather stations where they collect precipitation data, and these, the ones that are highlighted, are ones indicating observation stations where there was greater than an inch of precipitation reported. So we can start to see patterns of rainfall. We want to be able to then correlate that more specifically so we can see the intensity of storms and look at that with respect to the response behavior. And I think that was my last slide. So I'm good.
Okay. So I just joined Nest about a month and a half ago. And I'm from Texas. So I have been working with Amy and Brady at the Marine Marine Center. And what we're doing is using numerical models to track bacterial pathogens in estuaries. So this work is in its very early stages that I'd like to share with you. So this is an example of the type of model we use. You've probably heard a lot. You've heard a lot about models this morning. So the difference between this model and the models you've been hearing about is there's actual ocean physics in it. This is an example of model output. Can everybody hear me? Okay. So this is an example of model output from a hydrodynamic model we made of the Texas-Louisiana shelf. And so this is showing sea surface salinity. That's just one of the variables that this model will output. And so the color bar is showing sea surface salinity, and so this is the Mississippi River flow. I've done a lot of work here. There's two river outflow areas, one here in a top 5 bay, and then one on the peninsula. And so the blue colors, that's the really fresh water. The saltier water is this yellow color, comes from offshore. And so this model is telling us that there are these little eddies that are moving all the fresh water around on the shelf. And the wind is very important here, these arrows that you can't really see because of the projector, but those are showing the wind direction. And down here, this is showing river discharge. And so the other good thing about a hydrodynamic model is that it's three-dimensional, so you can look at any of these variables at any depth. So there are a lot of ways to apply these kind of models. A really useful thing to do is to look at particles and just see where the currents take particles. And so this is kind of what we're going to do for NETS. We're going to track pathogens using these particle tracking nodes. And so this is showing particles that are released at those river mouths. And you can see that a lot of particles kind of end up out here on the shelf because those eddies disperse them. There are a lot of particles that kind of bunch up here around the peninsula. And so this is telling us that the residence time of water here in the peninsula is long. It takes a long time for water to be flushed out of that area. And so that's what we mean by residence time. How long does it take to actually flush water from a region or from an estuary? How long will it take to replace old water completely with new water? And so this is of primary importance for the Department of Marine Resources in estuaries because that would give them an idea of like how to respond when there's some sort of bacterial pollution event. Like what's the how long to keep this place closed? And so after we learn about residence time from the model, we can also ask it other questions like why was the concentration high at the site in the first place? Like where did it come from and how long it took to get there? And so these are questions that the model can answer. So I've actually done a lot of field work in the Gulf of Maine. These are showing pictures of drifters that were released at the Merrimack River mouth. So maybe you guys know that area. And so typically when we release these drifters at a river mouth, they would end up in like a foam line, or like this one's in this debris line. And so what these lines actually are they're fronts. And it's where the river water meets the ocean water. And so there's this really big change in salinity across that front that can actually act like a wall. And so a lot of times you can have like any sort of pollutant that's released from the estuary can actually accumulate in this front and aggregate, and it can stay there for a very long time. So any sort of like harmful algae or bacterial pathogen. And so we wanted to learn more about these fronts in the Merrimack River. This was part of my PhD clip. Oh, that was horrible. Anyway, this is, if you don't know where the Merrimack is, this is Cape Cod, here's Cape Ann here. And the Merrimack is
100 meters cubed per second. It's about half, I would say half the discharge of Quebec. And so the way we approach this problem is by developing a model. So this is our model domain of the Merrimack River. This is again showing sea surface salinity. And so the green water is the freshest water. Here's the Merrimack estuary, and there's little jetties at the mouth. Here's Plum Island Sound here, and the entrance is here behind these panels. So they're showing discharge, river discharge here, and wind direction and magnitude here. And so the cool thing about the Merrimack, it's different from Mississippi, is that there are tides. The Gulf of Mexico has very small tides. And so this is a pulse plume. So every ebb tide creates a new plume. And this plume is very thin, so it will just kind of sit on top of the ocean water and go wherever the wind pushes it. And so typically, the river discharge will go to the south, and you can imagine that any sort of data we compared it to, any sort of like pollution is released from the estuary would move with this water and mix in the same way into the ocean as this fresh water. And so the question we were asking specifically here was about this tidal plume front. So how much water that's released behind the front actually reaches that front? And because things will accumulate at that front and propagate out with it. And so we actually went out and observed this. This is showing, I should explain it first. This is from an IR camera that we put on a balloon on a fishing boat here. So this is like a 26-foot boat, so just for scale. This is the plume front, and so this is at early ebb, just outside the Merrimack River mouth. And the IR camera is measuring the temperature difference between the plume and the ocean water. So the plume water is a lot warmer, it's lighter color. Ocean water is a darker color. Right here. And so you can see that there's these big sheets of fresh water that travel towards this front. And as ebb progresses, you see this even stronger. And so this was taken, this is not real time here, this was actually over about 2 hours during early ebb. And so we did the same kind of experiments with the model, where we released drifters at the river mouth here. And I'm going to play this animation, but I'll explain something first. So instead of plotting surface salinity here, I'm showing velocities, essentially. And so you can really see the fronts in this figure because they stand out. They're these darker lines. And so you'll see the tidal plume front come out of the estuary now. And so I've also added a little panel here showing the tidal height. And so there'll be little colored dots that appear on here that tell you when I did a dye release. And the colors will correspond to the dyes you see. Does that make sense? So you can do all this stuff numerically. So here I release dyes every 2 hours with drifters. And so you can see that there's a lot of variability when these drifters are released as to where they'll go. Most of the drifters released early in ebb will actually reach Plum Island Sound. And I don't track them all the way into there, but they would enter there. The drifters released later in ebb, those blue and green ones, they kind of just stay outside the mouth until the next ebb pulse pushes them offshore. And so, our goal, I don't have too much text up here. Our goal is to work with the Department of Marine Resources to develop simple metrics that they can keep measuring. And because these models can do a lot of crazy things that are very complicated. And so we hope that we can filter that down to something that's useful for the Department of Marine Resources, and by looking at environmental variables like wind and discharge and like ambient currents that can be easy to calculate. And I've only been here a month and a half, but I've already heard from a lot of people that this would be useful, some sort of like joint appointed postdoc between the Department of Marine Resources and the University of Maine. So I'm willing to do that, and I haven't sat down and talked to Cole in detail about it yet, but since our goals are with Damien and mine and Cole's, but we're online, so this would be a good thing we could try, and hopefully start working on regions that NEST might not get time to address. There are bigger problems. And so this is our first study site that we're currently developing a model for. This is The Wells Natural Estuarine Research Reserve is right here, and so I'm going right here. And so these are actually 3 river mouths here that I'm showing you. This is Wells here. And so we're going to model this entire thing. The Kennebuck River is up coast, which is off this picture, and the Gunquit is down here. And so hopefully we'll be able to resolve the estuarine dynamics in Wells and the Gunquit really well. But we'll also be able to look offshore and see things like these plumes that are out here and how those interact. And so that's where we are.